December 27, 2004. On that day, our solar system was hit by a very intense flash of energy. 50,000 light years away, at the origin of this fantastic lightning bolt, astronomers detect a strange object, a magnetar. In other words, a star that collapsed on itself with an incredible magnetic field. If it had been only 10,000 light years away from the Earth, the magnetar's rays would have blown away our atmosphere in a dozen seconds. Today, global warming. But tomorrow, are we threatened by a new ice age? Could the Earth's magnetic field change and leave us defenseless against the sun's wrath? What is the secret behind the mass extinctions which wiped out the vast majority of life on Earth at least 5 times? Could Apophis, that little asteroid, hit our planet in 2036? Gamma ray bursts are rays that come from the depths of space. This is the most dangerous and the least known of the cosmic hazards. From the dawn of humanity, men have looked up at the sky to read signs sent by the gods of a possible annihilation. But they were far from having the slightest idea that our planet, the Earth, isn't alone in its corner of the universe, and that it interacts with the whole cosmos. For example, today everybody is afraid of global warming caused by human activity. But this ignores the fact that the Earth's climate is decided outside of the Earth, in the complex mechanism that directs the planet's path around the sun. The result? It's almost certain that in the future we will have to face a new ice age. Here we are in a frozen library at minus 25 degrees Celsius. In these cold storage rooms, researchers from the Grenoble Glaciology Laboratory preserve these precious archives taken in the Arctic and Antarctic expedition after expedition. The concept is very simple. The deeper we dig, the deeper we go into the past. The drilling tool is equipped with a knife which drills the ice, and the shavings are evacuated by an endless screw. After weeks of drilling, we reach depths of over 3,000 meters and go back to over 250,000 years into the past. Once it's been cut, the ice cores give us remnants of the last ice age, which was 100,000 years ago. We call it the worm glaciation.
What does an ice age look like? It typically looks like this. The whole of the northern hemisphere covered in ice. 2 kilometers of ice on Canada. The alpine glaciers spread to Lyon. We could walk from England to France. The sea level was at 120 below. There was a different vegetation from today. In the future, we expect these conditions to come in 40 to 60,000 years.
The origin of an ice age isn't found on Earth, but much further in the sky. Remember this name, Milutin Milankovic, a Serbian geophysicist. He was the first to understand the astronomical causes of the great ice ages. And here are the planets responsible, our distant cousins, Saturn and Jupiter. These 2 planets are so big that their mass periodically deforms the Earth's orbit, making it more elliptic. Since the sun is further away, the energy we receive from it lessens.
The evolution of the Earth's orbit around the Sun causes the quantity of energy received at the surface of the planet to change with time. If we take winter snowfall at our latitudes, there needs to be enough energy during the summer to make it melt. If that energy is not strong enough, the snow is going to stay in the summer and form a glacier that is going to spread. This glacier reflects into space a big part of the Sun's energy. This amplifies the phenomenon, thereby creating an ice age.
And yet, the astronomical causes are not enough to start an ice age. What more is needed? In this laboratory, researchers are collecting from the ice the air that was around on Earth during the last ice age. What do we observe?
Ice formed 100,000 years ago shows less carbon dioxide in its little air bubbles than in ice formed between the ice ages. This crucial observation tells us that carbon dioxide has amplified astronomical parameters in order to enter into an ice age.
Less rays from the sun, less carbon dioxide to hold them back. These are the two conditions for an ice age. The next one, they say, will be in 60,000 years. In this very distant future, will humanity be forced to leave the Earth trapped under the ice? It's not certain, because the future might have a huge surprise for us. We're at the Atomic Energy Commission in Saclay, France, and this is Gilles Ramstein, paleoclimatologist. For years, he and his team have been developing computer models that show 3 possible scenarios in the future. Everything depends on us, and on the way we will continue or not to disturb the climate by sending carbon dioxide into the atmosphere. To begin with, the first scenario is, of course, utopic. It supposes that humanity, in its infinite wisdom, stops the damage right away. In this case, the cycle of the ice ages follows its natural course. As we can see, the next one starts in 50,000 years and peaks in 150,000 years. The second scenario, which is more realistic, imagines an important disturbance in the climate, but not a massive one. First observation. The Greenland ice sheet doesn't fare well in this situation, and a big part of it melts.
So we wait, time goes by, and we notice that nothing happens at 50,000 years. We should have an ice age, but absolutely nothing. At 150,000, we should be at the peak of the ice age, but still nothing. And we have to wait 220,000 years for glaciation to start, and to expand until it reaches its peak, 100,000 years later.
Finally, the third scenario. Man doesn't make any efforts to limit carbon dioxide sent into the atmosphere. And this time, Greenland disappears at the very beginning of the simulation.
And more extraordinary in this simulation is that there isn't a glaciation at 500,000 years, nothing at 150,000 years, nothing at 220,000, and nothing at 300,000 years.
That's right. The same reasons that caused global warming might avoid the next ice age. So we're not sure what to think of it. Should we be worried or happy? After all, it seems like good news.
It's probably good news for people living 300,000 years from now. But to get there, we would have to disturb the environmental system so much with a planet of 7 billion people, we would go through hell now for happiness in 300,000 years. I don't think it's the right choice.
But we're not there yet. For now, let's not forget that the Earth is first a planet before it's our home. Its logic is that of a planet, not our logic. Here's more proof of it. Let's imagine that the Earth is locked up in a cocoon. Since it's transparent, the cocoon lets sunlight in, but it's resistant enough to act as a shield. It would protect life by pushing away cosmic rays and deadly particles that hit our planet during solar eruptions. Well, this invisible shield exists. It's the Earth's magnetic field. Without it, life on our planet would suffer irreversible damages. For example, on March 13, 1989, an incredible solar explosion short-circuited Quebec's power plants and sent the country into darkness. Imagine the damage if the magnetic shield didn't exist. The only exception is the beautiful northern lights, created by particles from solar winds that manage to get through the barrier of our magnetic field. They disturb our radio waves and can be dangerous for astronauts. Now we're in the middle of a forest in the region of Orléans, France. Here, far from the disturbances of the city, very precise instruments called magnetometers constantly monitor the Earth's magnetic field. Because we know today that our magnetic field isn't stable, and it can even invert. These are two basalt fragments. One is 900,000 years old, the other one is more recent. Let's get them closer to a magnetometer. The more recent basalt has traces of the direction of the current magnetic field. North is north and south is south. But for the second one, it's the other way around. North is south and south is north. And now, look at the core of this rock. Like ice cores, it tells, in its own way, a part of Earth's history.
In this graph, we see that one of the main characteristics of the magnetic field is to invert. During these periods of inversion, the magnetic pole switches either from north to south or from south to north. In this rock core, which is 2 million years old, we can see 4 inversions which took place in that amount of time.
To understand why the Earth's magnetic field inverts, you have to understand where it's formed. Let's go to the center of the Earth. Let's imagine that we can pierce the Earth's surface and dive into the depths of our world. First, we go through the crust, which is about 40 kilometers thick. The temperature and the pressure increase. Then we reach the thickest layer, the mantle. It represents 80% of the Earth's volume alone. Soon, the mantle changes into a gooey and burning paste. This is the lower mantle, which is 2,000 kilometers thick. At a depth of 2,900 kilometers, we enter the liquid core, an ocean of iron and fusion. The liquid core is boiling hot because at every instant it has to expel to the surface the terrible heat of the center of the Earth. And finally, the very center is solid, paradoxically. It's the seed, a ball of iron with a 1,200-kilometer radius. It's all here. According to geophysicists, turbulences of the liquid iron core generate the Earth's magnetic field like a giant dynamo. And we're going to prove it, thanks to this experiment done at the Atomic Center in Cadarache, France. Here, researchers are simulating the conditions at the center of the globe. The experiment is starting.
The engines are on at a speed of 1,500 rounds per minute.
This cistern fuels a cylindrical vat in liquid sodium, the equivalent of the liquid iron core at the center of the Earth. To recreate the incessant movements that agitate the core, we use two turbines which turn in opposite directions with the power of a race car. The speed continues to increase. They're now making an awful racket. And soon, a magnetic field appears.
Okay, it's good. It is stabilized. It's starting. As you can see, the magnetic field is increasing. Slowly. It's very fluctuating, of course, because the movements of the fluid are chaotic in this experiment. There, it's off. It has a fluctuating average, but nevertheless a north-south direction. Both directions are possible, but in this case, it decided to go north-south.
North-south, just like on Earth today. The liquid sodium's agitation created a magnetic field by a dynamo effect. But if we continue the experiment, the magnetic field ends up inverting.
There, it just went into the south-north polarity, where it's going to stay for an unpredictable amount of time. Notice that before it goes back to a north-south polarity, it becomes very weak before increasing again on the other side. Why do inversions take place? Well, we don't know. The magnetic field has two states which are both equally probable, and the system can choose, because of its spontaneous fluctuations, if it wants to be in a south-north state or a north-south state for an unpredictable amount of time, and it can wait for the next inversion for an unpredictable amount of time as well.
At the moment of the inversion, the magnetic field's value is close to zero. Should we be worried about this?
Yes and no. What I demonstrated here is simply the main dipole component of the Earth's magnetic field. There are secondary components, and during an inversion, these secondary components are probably preserved and even enhanced, which has allowed people to think that the magnetosphere continues to exist during an inversion and continues to protect people.
In short terms, our magnetic protection never disappears. Yet, these periodical fluctuations must certainly have consequences. But which ones? This is the Magnetic Observatory in Saint-Maur-des-Fosse, France, which moved out of Paris in 1901 because of the electromagnetic disturbances caused by the arrival of the tramway. From then on, researchers have been measuring the short-term variations of the magnetic field on archaeological relics. And what they found is surprising.
We found some very astonishing relationships between the variations of the intensity of the Earth's magnetic field and certain events in the history of human civilizations. This isn't a direct relation, it's an indirect relation. The link between the Earth's magnetic field and the history of the civilizations is the climate. For example, this is a fragment that carries the trace of one of our geomagnetic events. It is the fragment of a pavement tile which dates back to the 14th century. And the 14th century is the beginning of the Little Ice Age which lasted until the middle of the 19th century. So here, it's an exceptional geomagnetic and climatic event that happened in the last millennium. These are bricks that carry the trace of another geomagnetic event that dates back to the 8th century AD. It was marked by a drought in Central America. According to certain archaeologists, this period of drought caused the fall of the Maya civilization.
Identical correlations have been established between these peaks in magnetic intensity and the downfall of the Akkadian Empire in Mesopotamia around 2200 BC, or the downfall of the ancient Egyptian Empire around the same time. In a more distant past, 40,000 years ago, the fluctuations of the Earth's magnetic field may allow us to answer an enigmatic question.
40,000 years ago, the intensity of the field lowered considerably, so the magnetic field wasn't protecting us like it usually does. It is outstanding because at this same period, 40,000 years ago, the Neanderthal man disappeared. This disappearance still hasn't been explained. This magnetic field hypothesis stays plausible because we can assume that when our magnetic field is very weak, the ozone layer, which protects us, diminishes considerably. So we can imagine that the important penetration of ultraviolet rays affected Neanderthal man greatly and caused his extinction.
But let's not put words in researchers' mouths. The fluctuations of the Earth's magnetic field don't write alone the history of civilizations. Mankind is at the center of the stage. But the theater is also important, and let us remember that the theater is a planet. The Earth, seen from space, is radiantly beautiful, like a jewel. The deep blue of the oceans and the thick endlessness of the clouds. It's certainly beautiful, but there's also something that makes it dangerous. Its insides are on fire. Thousands of degrees of infernal heat that has to be expelled periodically by any way possible, unfortunately for the miserable creatures crawling at its surface. For the past few dozen years, geologists have been discovering the devastating power of a giant volcanism, which they call hotspot volcanism. These are eruptions that come up from the very hot regions of the Earth's mantle like a huge blowtorch. And yet, on the planet, a region still bears huge scars from this, the Deccan Traps, in India to the south of Mumbai. To get to the location of the famous traps, we took the highway from Bombay to Pune. Then we took the byroads to get to the Mahabaleshwar Plateau at 1,500 meters in altitude. There, our guide asks us to follow him on a promontory. And all of a sudden, there are the traps, as far as the eye can see. In Swedish, the word trap means stairs. It describes the site very well. These mountains look like stairs, but giant stairs. It's piled up lava, the product of a series of gigantic eruptions 60 to 70 million years ago. And we knew this because this is why we came here. But what a shock when you're in front of it. 2,400 kilometers of lava piled up above the ground on a surface of 500,000 square kilometers, the size of France. Obviously, hotspot volcanism isn't an ordinary kind of volcanism.
Why is hotspot volcanism so violent? There are two things: the volume of the lava and the speed at which it comes out. The volume of the lava is gigantic because probably this volcanism comes from the very depths of the Earth's mantle. At almost 3,000 kilometers under our feet, an instability forms itself, sort of like in those famous lava lamps, those lamps from the hippie generation where we saw a ball of red wax lift up, heated by a light bulb. When the head reaches the surface, it breaks the surface and erupts, and it will have a huge volume. But the question is, in how much time? The more our work has progressed, the more we realize the lava flow arrives in a very short amount of time, injecting a horrible amount of carbon dioxide and especially sulfur dioxide, which created acid wells, a winter, and then a period of warming. In sum, a horrible environment which led to the extinction of the species.
The history of life on our planet has been marked by terrible catastrophes. To convince you, let's use an image. Let's follow the boat of life on a 500 million year journey.
There are 5 big catastrophes, 5 periods where, on a very short amount of time, geologically, an important part of life on Earth disappears. The first of these catastrophes, this tsunami, which is going to affect the extinction of the species, happens 440 million years ago at the end of the Ordovician era. Life starts again, and another one hits us in the face 360 million years ago during the Devonian era. And then life starts again. It seems to have leveled off. Here we have the impression that our boat is sailing on a calm sea. But no, it isn't a calm sea. There are 2 extinctions which are the most violent in the history of life. Extinctions which, globally, are going to wipe out 95% of the species, maybe 99% of life on Earth. Which means that life was 1% away from being completely extinct. Everything will need to start again from the beginning. Can you imagine the billions of years it would have taken? But that 1%, our actual ancestors and the ancestors of all the life we see on Earth today, and it starts again, better than before, and the diversity is greater than during the primary era. But tough luck, at the end of the Triassic period, 200 million years ago, there's the 4th shock. But it starts again, and it goes even higher. And as we are developing fantastically, the 5th extinction arrives, the one everyone knows, the end of the dinosaurs. 65 million years ago, the extinction at the end of the Cretaceous.
According to Vincent Cortillo, all of these extinctions, except the one of the Ordovician, are linked to traps that have been located. In particular, the famous extinctions of the dinosaurs 65 million years ago was caused by the giant volcanism of the Deccan and the impact of a huge asteroid in the Gulf of Mexico.
I don't have any more doubts that the impact took place, but it only added something worse. To an event that had already started and that happened to provoke all of the other extinctions without the intervention of an asteroid.
And every time, life came out transformed and shaken by these huge extinctions. Nothing will be the same. Which leads us to the question, when will the next trap be?
I can start by scaring you, and this is what I'm going to say to scare you. We calculated the average time between 2 traps. There's a whole series. I only spoke about the most important ones. But there's a lot more. There have been about 12 of them in the past 500 million years. On average, there's one every 30 million years. And when was the last big one? The last big one was the Ethiopian traps. It's the plateau on which the capital was built, Addis Ababa. How old is that trap? It's 30 million years old. The last big trap was 30 million years ago. There's one every 30 million years. The next one might be tomorrow. Tomorrow with a margin that can cover millions of years. When something will rise from the depths of the planets, it will probably rise at the speed of a few dozen centimeters a year. It will probably cause a bunch of seismic and volcanic activities that we will probably see 1 million years in advance. So we have the entire lifespan of the human race to see the next one coming.
Let's go back to the asteroid that contributed to the extinction of the dinosaurs 65 million years ago. Today, astronomers have identified the one responsible. A 10-kilometer fragment from the Baptistina family, a group of bolides that escaped from the asteroid belt, which roams not far from our planet. The question is, could this catastrophe happen again tomorrow or after tomorrow? The answer is maybe. Blockbusters have not failed to use this argument. Jean-Yves Prado, an engineer at the Space Center in France, contributes to the work of several international organizations which study near-Earth asteroids, meaning asteroids that are likely to cross the Earth's orbit. 6,674 have been identified, and 1,086 of them are potentially dangerous.
To be a threat to the planet, the asteroid has to be bigger than 1 kilometer in diameter. There are 1,000 that have been discovered, and none are on an impact trajectory. There are still a few dozen that we have to identify. We're hoping that in those few dozens, there are none that are on an impact trajectory as well.
A planetary catastrophe seems out of the question for now, but the risk of an impact with a smaller object still exists. In December 2004, a 270-meter-long asteroid named Apophis worried specialists who feared a collision with the Earth in 2029. But the following year, the alarm was lifted. New observations showed that Apophis is going to miss the Earth by 32,000 kilometers, so we relaxed. But maybe we're wrong. We're now in Nice, France, at the French Riviera Observatory, and here is Patrick Michel, one of the best specialists on asteroids in Europe. He will explain to us how we missed a small detail when we believed that Apophis wouldn't hit us in 2029.
This is the small detail. It's called a keyhole. Here I drew the Earth with the Moon here. Apophis is going to pass less than 32 kilometers away. The distance from the Earth to the Moon is 400,000 kilometers. And the small detail that we're forgetting is that there is a little zone of uncertainty, 600 meters wide, which Apophis might go through. And if Apophis goes through it, it will crash into the Earth in 2036. Otherwise, it will miss the Earth by several million kilometers. The problem is, to predict if it's going to go through this tiny zone, we would have to factor in elements that we do not know how to calculate yet. Thus, the uncertainty.
Let's imagine the worst-case scenario. What would be the consequences of an impact with Apophis? They would be terrible. By traveling through the atmosphere, the asteroid would be heated at 1,600 degrees Celsius. The impact would radiate an energy that is 34,000 times more powerful than the atomic bomb that was sent on Hiroshima. Today, NASA considers that the chances of getting hit in 2036 are 1 against 135,000. This is reassuring, but in the case of danger, what could we do? The first solution is to pulverize the bolide. Of course, it seems like an effective method, but it's risky because of pieces that might fall to Earth.
It is risky, in fact. It is not the right solution at all, because when you blow up an object, you don't know in how many fragments it will end up. You can get very big fragments, which will fall on the Earth anyway, so that's not a solution. Or maybe thousands of very small fragments, which will also reach the Earth and spread out, so that it's not the right solution either.
For most astronomers, driving the bolide off its course seems like the most reasonable solution. In 2005, NASA tried shooting an object at a little comet named Tempel 1. This technique could drive an asteroid the size of Apophis off its course. But there's yet another method.
The other solution is what we call the gravity tractor. The idea is to put a satellite next to the asteroid, and the mass of the satellite is going to attract the asteroid. That way we can drive it off its course and avoid a crash.
The prize for imagination goes to this procedure, which consists of sending a giant umbrella to the asteroid.
The method we could use is to cancel out one of the natural effects that takes hold of the asteroid. The surface facing the Sun is heated by the Sun. This phenomenon creates a little force which contributes to the attraction between the planets and the asteroid. So if we cancel out this force, we change the trajectory. It is a very weak effect, but if we drag it out over several years, we can deviate it by several hundreds of kilometers. So if it originally had an impact trajectory, this can change things entirely.
Let's not cry wolf, but let's keep it in mind. This is why the International Society of Astronautics has had the idea that a line of permanent observatories to watch asteroids should be built. The important thing is to see them coming from far away. There is yet another danger, another cosmic event which could have disastrous consequences if it touched the Earth. It's what astronomers call gamma-ray bursts. First, we would see a big star shining in the middle of the day. In the next second, the entire sky would become white, burnt by gamma rays, which are high in energy and deadly. And the ending would be tragic. To look into this, we went to Washington, D.C. This is the Goddard Space Flight Center, only 50 kilometers away from the capital, one of NASA's many research centers. The team you see here work constantly on the data sent by SWIFT, a space telescope which hunts for those mysterious gamma-ray bursts. As a matter of fact, here's one now.
Well, about 3 hours ago, just before you arrived, we had a gamma-ray burst detected by SWIFT. And here on the screen is the image from this burst. It's just 3 hours old. And we detect about 2 per week. We don't know yet the distance to this one. We don't know the energy, but we will find out over the next few days. And about 100 times a year, we have such a discovery.
So, the sky is constantly bombarded by gamma-ray bursts, and some of them are real monsters.
This is one of the most famous gamma-ray bursts of all history. It's 080319b. And it was so bright that you could see it with your naked eye without any telescope. And yet it was 7.5 billion light years away. So it was halfway to the edge of the universe.
But what is a gamma ray? Well, it's very easy to understand when you look at the electromagnetic frequency spectrum.
Gamma rays are the shortest wavelength part of the electromagnetic spectrum. So you start with radio waves, and then you go through infrared, visible, X-rays, and gamma rays. Radio waves are very long waves. Gamma rays are very short. And the shorter you go, the more energy these light waves carry. So gamma rays have a lot of energy. They're actually dangerous. We use them for medical imaging, but nuclear weapons, nuclear bombs also produce gamma rays.
Big bomb.
Gamma-ray bursts were discovered accidentally during the Cold War. At the time, they thought they were Soviet atomic explosions. Then they understood that they were coming from much further away, from the depths of outer space. Some imaginative astronomers believed that a kind of interstellar war was going on. This was at the same time that the famous Star Wars saga was released, of course. To Today we know that gamma ray bursts are caused by exploding stars. Some are short, lasting only fractions of a second.
The short bursts, we believe, are caused by massive stars that are orbiting each other. Actually, they're compact neutron stars. And as they orbit each other, they lose energy in their orbit. Eventually, they collapse, they coalesce in a fiery explosion. When these stars hit each other, they produce instantaneously a black hole. And then there's gas that's left over falling onto this black hole that produces the gamma ray burst.
Long bursts, which last several seconds, are caused by the explosion of huge stars, 40 to 100 times bigger than the Sun.
And a massive star like that evolves in a different way than our Sun. The core nuclear fuel burns up quickly, and then it collapses. And it collapses to a black hole. And when that happens, all of the gas of this star starts falling into this black hole. There's a tremendous amount of energy falling into a tiny amount of space, and it's that explosive collapse that produces the gamma ray burst.
Don't worry, most of the time gamma ray bursts happen too far away for us to worry about. And their rays spread out into the universe. Yet, in the distant past, the rays from a gamma ray burst may have hit our planet and left some major consequences. Let's take our boat of evolution backwards. We saw 5 massive extinctions. Geologists are able to explain the last 4. But the first one couldn't be explained. What if it was a gamma ray burst after all? To answer this enigma, we went to Topeka, the capital of Kansas. This is Brian Thomas, astrophysicist and professor at Washburn University. He's going to tell us what happened 450 million years ago.
Our hypothesis is that a gamma ray burst occurred about 450 million years ago over the southern hemisphere and caused the extinction of the trilobites, which were the dominant life form at the time. Our evidence for this is primarily that organisms, trilobites, that lived at the bottom of the ocean were more likely to survive past this time period, whereas those that lived at the top of the water were more likely to go extinct. This fits very well with a radiation event. Those at the bottom are protected by the water above them. Those at the top are not protected.
Thanks to the SWIFT satellite, we now know that gamma ray bursts come from everywhere in the universe. So, could the catastrophe of yesterday hit us tomorrow? And how can we evaluate this threat?
It depends entirely on the distance to the gamma ray burst and if the gamma ray burst has its beam of gamma rays aimed in our direction. The safety distance within which it becomes a real threat is about 6,000 light years.
In other words, if the gamma ray burst takes place less than 60 million billion kilometers away from the Earth, then it will certainly be a catastrophe. And in this case, what would be the scenario? First act, the flash. But what happens next?
The next thing is that the gamma rays would change the chemistry of the upper atmosphere and cause the ozone layer around our Earth to be depleted or to go away completely. That allows ultraviolet light to come down to the surface and would kill organisms on the surface.
Very quickly, the atmosphere would be filled with nitrogen dioxide, a brownish-reddish gas similar to the one caused by car pollution.
The atmosphere would become darker than we see it today because nitrogen dioxide is produced. And this is a gas that absorbs visible light and looks very brown. If you've ever stood in downtown Los Angeles and couldn't see the mountains even a few kilometers away, That's because primarily of nitrogen dioxide. It absorbs that light and makes the atmosphere dark.
But the worst is yet to come. The gamma rays would cause what the military call an EMI, an electromagnetic impulse, which would destroy every electronic circuit in an instant. Our civilization, which is based on electronics, would crumble. This is William Forstchen, science fiction author and professor of military history in North Carolina. In a recent novel based on reports by military experts, he imagined the consequences of an electromagnetic impulse caused by the explosion of a nuclear bomb above the United States. The situation would be identical, but much worse if it was a gamma ray burst.
The very first effect would be rather startling, but commonplace. The electricity turns off. All the power for the city of Paris, for example, shuts down. Air traffic control shuts down. Airplanes in the air will start falling from the sky. Hospitals and nursing homes, retirement homes, the power goes off. All the machinery that keeps our elderly alive goes off. At the end of the first day, every major city will become uninhabitable. There's no water, there's no sanitation, no medical facilities will work. For example, people with pacemakers. The pacemakers most likely will short circuit. People requiring medication every several hours, they'll start dying. People in hospitals and retirement communities will be suffering terribly. What happens if it's in the winter? No heat. In the summer, no air conditioning. Within a day, your city becomes uninhabitable. After a week, the city is now uninhabitable. 10 to 20% of the population might already be dead. There is no longer any food. Where do you go to get your food? In other words, every major highway will be filled with refugees, desperate for food, desperate for clean water, desperate for protection. Let me present you with another question. What do you do with people in prisons? Do you leave them in the prison and let them die? Do you shoot them or do you let them go? These are the type of moral questions every person would have to face. It will mean a vicious world where people will have to fight to survive. After a year, the survivors, those few that are left are the ones that are tough, are lucky, know how to band together with other people, or are extremely vicious. I mean, in the most dangerous way possible. Gangs and such might survive. Citizens who know how to protect themselves over the last little pieces of food that might be available.
And it's not over yet. Here's the third phase of the extinction.
The nitrogen dioxide is produced mainly in the stratosphere, and it stays there for many years. And as a consequence, it would reduce the sunlight that reaches the Earth's surface. That would lead to global cooling and probably an ice age.
Once again, the chances of such a catastrophe happening are very low, but not entirely inexistent. Around 7,000 light-years away from the Earth, which isn't that far after all, there's a huge star close to the end of its life. Eta Carinae, a star that is 150 times more massive than the Sun.
Well, we know that Eta Carinae is the type of star that might produce a gamma ray burst. The main question is whether or not the rotation axis of the star is pointed towards the Earth. There's some uncertainty about this. If it is directed at the Earth, then it's within a distance which would cause major effects at the Earth. If it is not directed at us, then we probably would see it more as a normal supernova, and it's too far away for that kind of event to cause any major effects here.
Let's say it again. Today, we couldn't do much against a gamma ray burst. Should we really worry about it? Fortunately, as we've seen, the risk is low. But there's more. On several occasions during its long history, life on Earth has crossed the path of cosmic hazards. It has often been wounded, but never killed. cosmic hazards are not only destructive, they also create. The explosions of massive stars are dangerous, but they also spread out into space heavy atoms, which construct the molecules that are the basis of life. As for the cosmic rays that are sent by these explosions, they cause mutations in the DNA of the ocean. And sometimes it's for the best, because it's perhaps one of these mutations a few million years ago which allowed a great ape to stand on its hind legs and evolve one day into Homo sapiens.